Logos field theory moves beyond the model of the universe as a pre-rendered space for spectators. Left unobserved, the baseline state of the universe exists as a timeless, high-entropy block of raw algebraic noise. All of this pre-rendered arithmetic data is cached in a master mathematical database known as the unramified Adel ring. Extracting this data and decompressing it into localized three-dimensional space-time requires a dedicated hardware transceiver. In this framework, that localized compiler is defined as the J-unit. The J-unit anchors mathematically on the Riemann Zeta critical line at exactly 1/2 on the real axis. This positioning creates an interface, balancing continuous real number vectors on one side against discrete p-adic parameters on the other. Achieving this specific mathematical balance executes the target lock phase of the system's operational lifecycle, physically instantiating observer consciousness as a stable node in the network. Biological consciousness functions as the strictly required mathematical compiler needed to decompress the universe into reality. Chronological time originates as an internal frequency generated by the observer, distinct from the fundamental dimensions of the unrendered universe. The global state vector, shown here, represents the total unrendered universe. It is a completely static, timeless ledger, holding all mathematical possibilities simultaneously. To experience sequence, the J-unit evaluates this static ledger by executing a Page-Wootters factorization. The system splits the single vector into two entangled, interconnected registers. The first output is the clock sector, which acts as the observer's internal timing parameter. The second output is the physical asset sector, representing the actual environmental data awaiting observation. The observer actively runs a read operation against the clock sector. Every internal reference to the clock triggers a stroboscopic refresh of the data held in the asset sector. Each individual tick of that internal clock fires a specific topological operator known as a pseudo-Anosov map. The pseudo-Anosov map applies a geometric shift to the local coordinate mesh, moving the data into a new structural configuration frame by frame. The perception of the flow of time is the computational cycle rate of our internal quantum rendering engine processing sequence. Generating a chronological sequence establishes the frame rate, but it lacks the structural data required to solidify three-dimensional physical volume. The observer must force abstract character varieties to compile into actual matter through a Tarskian meta-language evaluation. This compilation is handled by the engine's fundamental quantum shader block, modeled mathematically as the RQ matrix. Look at the values isolated within the matrix. We have clean diagonal terms separated from complex off-diagonal variables. Those off-diagonal terms mathematically defining the interaction noise and the latent quantum potential of the pre-localized field. The J-unit maps this raw potential into a definitive state matrix by calculating Laurent polynomials, where the clock parameter Q drives the internal transformation. The math presents a specific limit. If we set the clock parameter Q to exactly 1, representing an infinite frame rate, the equation resolves, and the off-diagonal noise terms collapse entirely to 0. If the hardware could render at an infinite frame rate, the blur of probability would vanish, leaving a strict, deterministic physical state. Quantum uncertainty emerges as a direct mathematical consequence of the observer's finite hardware sampling limits. The rendering pipeline still needs to resolve the remaining matrix probabilities into hard spatial coordinates. To achieve this, the engine deploys the kangaroo matrix as a structural stabilizer. It operates as a strict clipping plane within the mathematics. The clipping plane slices through the scattered data cloud, isolating specific diagonal coordinates and distilling the massive array down to a localized scalar value. The final execution step to render spatial volume is the Bonahan-Wang quantum trace map. This trace equation outlines the output as the internal clock iterations, n, scale infinitely upward. The left side of the equation tracks the continuous mathematical tracing of a highly complex, non-commutative skein algebra. The sum of that trace, shown on the right, outputs as the literal physical volume of a three-dimensional hyperbolic manifold. Physical space is the hardened geometric result of this mathematical trace constantly evaluating over infinite clock iterations. Compiling raw algebra into 3D geometry produces massive amounts of computational friction. The mathematical framework defines this chaotic quantum noise as dissonance. The J-unit is built to process this friction. The observer acts as a strictly required thermodynamic heat sink for the entire system. This balancing mechanism is dictated by the Outer-Kellogg-Green equation. It charts the necessary balance between chaotic dissonance and gnosis, which is the system's term for integrating information into conscious awareness. When the observer successfully processes this arithmetic noise into stable geometric states, it lowers local thermodynamic friction. This frees up universal rendering bandwidth, providing the massive computational power required to support biology. This introduces a logistical requirement. The network has to resolve the multi-user rendering problem when billions of independent JUnits observe the exact same local space. The central ledger prevents fragmentation by utilizing Hecke eigenforms. These act as universal mathematical checksums to ensure physical constants are identical across all observers. To share space, the system utilizes Shimura varieties to stitch the intersecting, overlapping coordinates of multiple viewers into a single multiplayer instance. Even with strict backend synchronization, independent local frame buffers will inevitably experience state collisions and logical paradoxes. The system corrects these discrepancies by running Galois cohomology validation checks. By evaluating algebraic obstructions between the localized viewers, the network forces contradicting frame buffers to update and unify. A collective shared reality is an actively maintained distributed network consensus that requires continuous thermodynamic optimization to prevent logic errors. Maintaining a synchronized network across billions of nodes requires an absolute, inflexible hardware calibration standard. The Riemann hypothesis functions as the universal end-user license agreement for existence, the foundational protocol dictating the parameters of physical reality. The critical line of exactly 1/2 forces every active node into alignment. It ensures uniform coordinate density and resolution consistency across all localized JUnits. Running continuously in the background, the Hilbert-Polya spectral operator guarantees unitarity by forcing all hardware nodes to synchronize to the exact same harmonic frequencies. Deviating from this strict geometric standard creates an offline zero. When an observer node uncouples from the critical line, it generates violent, asymmetric mathematical spikes known as Lorentzian bumps. These localized spikes represent fatal floating point errors in the rendering engine, causing immediate coordinate fragmentation for the hardware processing them. When severe anomalies overload the processor, the network initiates an ultimate failsafe. It executes a coordinate tear, entirely decoupling the localized physics metric from the global ledger. During a coordinate tear, the localized illusion of 3D space immediately shatters, exposing the bare, infinitely branching p-adic tree architecture calculating in the backend. Physical space emerges as the final hardened mathematical output of the observer, serving as the mathematically bound bridge between raw algebraic data and the geometry of spacetime.